Okay, so today we're going to be looking at finding the area of a polar region by understanding our polar graphs. So let's take a look at example 1. So that means we are going to do an example 2. But before we do, I want to give you the formula for finding the area of a polar region, whether it be the whole graph or a partial part of the graph. So let's take a look at what that formula is. So before I give that to you, just a little heads up. Let's say we take a look at our polar coordinate system. Take a look at its graph. It's based off of circles with a radius of r. Okay, and it goes around at certain angles throughout our polar coordinate system. Okay, so in our polar coordinate, we have r comma theta. Theta is really important. Now, when we were looking at finding the area of a circle, we said that area is by r squared. Pretty simple. Okay, now, if we're looking at a particular piece, okay, of our curve, and we have what's called a radius, then you may remember from geometry class that we have different sectors of a circle, okay? So basically what I was drawing out is like I have quarter circles, so you just divide by 4, okay, from this formula, but it's just basically some sort of portion of your circle. So let's say we kind of like narrow it down a little bit more towards like this angle here, like you see in this example, how it's kind of measuring out some sort of angle there for theta. And if that's the case, then you need to take a portion of the circle. So you would multiply it by whatever portion that is. Now, since we're in radians, we would measure out, okay, what that is and divide it by 2 pi. So, well, what measure do we have? We're going to leave it in terms of theta for our formula that we're going to be using for area of a polar region. So, if you take a look at this, okay, so like if we have a simplification, it's going to be 1/2 r squared theta. That is our area. You may actually remember using this in either geometry or in algebra 2. So let's take a look at the formula we're going to be using in BC Calc. Okay, so if we have a curve r equals f of theta, and we're looking at finding a particular area of the region between that curve, and we are saying the origin, okay, which is usually referred to as the pole in the coordinate system, but that's okay, because remember, you can superimpose them. We're looking at for some value of theta, and you can actually say theta sub 1 here, and theta sub 2 there, because they are going to be angle measures. But for our textbook that we have here, they use alpha and beta. There's alpha and beta if you've never seen them before. Okay, so that's a way in which I write them. So you can write it either way. So the area is integrating that 1/2 r squared d theta, because the theta value is changing throughout your whole graph. It's not going to stay a particular fixed value because theta is going to change throughout the graph. So that's our formula for area. And of course you can take out the 1/2, okay, in front. So you can be using just this. And it's also described that r is f of theta, so you can see that over here. Instead of having like the r squared, they wrote f of theta squared, but it's the same thing, okay, either way. that you see it written. That is a very large alpha. That doesn't look anything like alpha at all. Let me change that. That was a little sloppy. It's still sloppy, but not too bad. Okay, so let's get to our example now that we have our formula. Hopefully you wrote it down. I'm going to leave the formula there in case you need to still jot that down as I read the example. Hopefully you're writing down the example as I'm reading it through though. Find the area of the region in the plane enclosed by the cardioid r equals 2 times the quantity of 1 plus cosine theta. Now, a cardioid is a particular type of limacin. And basically, whenever I graph these, they kind of look like a lima bean. So it's kind of easy to remember it's a limacin. It's spelled like a lima bean. It's pronounced limacin. And I found out that it was French. And it's a French word for snail. So I guess, like the shell for a snail kind of goes arounds and arounds. So some of our curves tend to kind of look like that in some way. And the cardioid type for a limacin is heart-shaped, and it's different kinds. And I had lessons on this from prior courses, so maybe you have heard of some of the other ones. Like there's one with an inner loop, and then we have our rose curve that has petals, which I think you've seen before. If not, you'll definitely see it in like some of these problems. So let's get to this one. You should have had enough time to copy as I was talking about the background to this problem. Okay. So in this particular problem, when you start to graph a polar equation, you start by a polar coordinate where theta is 0. So if you plug in 0 for theta to figure out r, you would just replace theta with 0. Cosine of 0 is 1. And 1 plus 1 is 2. So we really have 2 times 2 here, which is 4. So what that means is at an angle of 0, it has a radius of 4. So the first point that's plotted was actually out here. Okay? And then as you go through your graph, so let's say you do your quadrantal angles. So let's say you put in pi over 2. Okay? So the cosine of pi over 2 is 0. And if that's the case, we have 0 plus 1. I didn't actually fill in the rest of that before. And 0 plus 1 is 1, and 1 times 2 is 2. So we have a radius of 2. So at pi over 2, we have a radius of 2. And if you look at the graph, it was graphed here. Now, whenever you plot from one point to next, you should really have a lot more points, but you always make a curve that is counterclockwise, okay? And you do so where it's like concave down, okay? You don't want to come this way between the 2 points, because if you finish that circle, you're really going around clockwise, okay? And you don't want that. So if you're coming between these 2 points, okay, I was trying to draw, but the eraser keeps getting in the way. Like these 2 points, instead of connecting them that way, you connect them this way. It makes more sense because you're also going around like all the angles counterclockwise. Okay, so that's how it would be connected. So you would just keep connecting more points. So let's try more points. So let's try pi. If you plug pi in, we have -1 plus 1, so that's 0, times 2 is 0. So we end up, okay, over here. So we're at the pole, but we didn't actually finish the whole region, this whole graph of a cardioid. So that's what's indicating we should keep doing. So let's try 3 pi over 2. Okay, at 3 pi over 2, you plug it in for cosine, again, 0. Okay, if it's 1 pi over 2, 3 pi over 2, etc. So r is 2. So that's down here. So keep going counterclockwise. And let's go back to 2 pi. So what we're establishing here is that to finish the entire region, we went from 0 to 2 pi. That's your alpha and beta. Let me just prove to you it was to 2 pi. So cosine of 2 pi is going to be 1. And we plug that in. And we end up with 4. So we're back to this point here that we started with. So it is from 0 to 2 pi. Area, okay, that we can pull out the 1/2 is going to be of r squared. Here's r. We're going to square it. Here's our d theta. And we have our integral already set up. So in this particular case, what I would do, I plug it into the graphing calculator. Now, when I plug this in, okay, you can plug it in exactly like I did and make sure you multiply your answer by 1/2. Or if you're doing a calculator, it might be best to leave the 1/2 there. Okay, so there's multiple ways to plug it into your calculator, and you should get 18.850. Okay, so it comes out to 18.849555592, etc. It actually has an exact answer of 6 pi. If you use like a double angle formula within your integral by hand, you can get the exact answer. But for most of these problems, you are going to be able to do it with a graphing calculator. Other types of problems, you're just actually setting up your integral. So it's really important that you know where it starts and where it ends. Okay, so another important one where we need to know where it starts and where it ends is to find the area of the inner loop of the limacon, r equals 2 cosine of theta plus 1. Okay, so you need to know where your inner loop starts and where it ends. So knowing how to plot the points, or actually like plugging into our polar equation, it should help us discover the inner loop. Okay, so I mentioned about using the graphing calculator in the last one, and you're definitely going to need it for this one as well, because this is going to be an approximate answer. It's not going to work out nicely to be equal to 6 pi. So while we have our graphing calculators out, we can use it to see how it's being graphed and where that inner loop actually is. So I'm going to pull up my graphing calculator. I can't do this like in a video kind of thing because I don't have like a camera option. I have picture option. So do make sure you take a look on the graphing calculator to see how it's graphed. Okay, so you do usually want to start out with a standard window, so Zoom 6, and that's the one on the left. But you don't really see it very clear. What you do see is like where it starts to be plotted. So it seems to have a radius of 3. Okay, when a theta is 0. So it starts all the way out to the right where there isn't an inner loop. And then as it, it starts to go around, it creates an inner loop and then comes back around. So I wouldn't be thinking that it's angles that are near or very near 0 or very near where theta is 2 pi. So let me take this one away and focus on the other one so you can see a little bit clearer that inner loop that is created. So Let me see if I can, yeah, I can move it over, yay. So, what I would do is actually try to figure out what's going on around pi, okay, or pi over 2, to see a little bit more of like what the answers would be. So let's do that. So when theta is pi over 2, okay, so cosine of pi over 2 is going to be 0. And I don't know there we go. It's a little sloppy. And we end up with radius of 1, okay? And so that makes sense. It seems to be crossing here at 1. So it seems that it's after pi over 2. So let's see if our angle measure is between pi over 2 and pi or not. So start with your quadrantal angles just like I did the other problem. So if you plug in pi for cosine, you get -1. Okay, so now it's -2 plus 1, that's a -1. So at pi, what happens, okay, here's pi, you don't plot here when r would be 1, you'd be plotting here where there's a -1. And that's already like the center, I shouldn't say the center, but that's part of the inner circle. If you saw it graphed, it went from this point around. So it started somewhere before, over here, before it got to that point when theta was pi. Okay, so we're getting somewhere that our region that we need to find the area of is somewhere between pi over 2 and pi. So do look to have like reference angles of pi over 3, pi over 6, and pi over 4. Okay, so let's talk about being in quadrant 2. Okay, if let's say we subtract pi over 6, okay, 6 minus 1, it's 5 pi over 6. I forgot the pi. There it is. If you have reference angle of pi over 3 and you subtract it in the second quadrant, it's going to be 2 pi over 3. And if you're using a reference angle in the second quadrant, and if you're wondering what I'm doing, I'm just taking pi and I'm subtracting these angles. Don't forget to make a common denominator before you subtract anything with fractions. So pi over 4, okay, 4 minus 1 is 3, so it's 3 pi over 4. So if you're wondering what I was talking about, that's pretty much what I was doing. Trying to find the angle measures that reside in that quadrant between pi over 2 and pi. Okay? So now that you have an idea of what I was getting at, let's actually plug it into our function. So the easiest one to do here that doesn't have anything to do with radicals would be the 2 pi over 3, okay? Because the cosine of pi over 3 is 1/2. And cosine does happen to be negative in that quadrant, but I'm multiplying it with 2, I get -1. And when I add 1, we get 0. So from here, okay, to 0, that may be where we're starting our inner loop. Now you can actually move in and get a better graph. This is zoom 4, but you can also zoom in even more. And you can see that it is starting at the pole. So yay! We figured out the first angle where our inner loop starts. And it just so happened to work out nicely because, like I said, cosine pi over 3 we know is 1/2, so we're able to use that as a good place to start off. Now, once you know that, you can see how that lemmason is pretty much balanced and symmetric. So your best bet is to guess that its reference angle of pi over 3 is also being used in the third quadrant. Okay, so remember the next point that was plotted was over here. So it created that curve. We needed to figure out how to come back to the pole and at what angle. So like I said, third quadrant, this is where we do pi plus our reference angle. So if we think it's pi over 3, okay, that means we would be using the angle of 4 pi over 3. Okay, 3 plus 1 is 4. And once again, reference angle pi over 3 is going to give 1/2 for cosine. It's negative in that quadrant. So 2 times a negative 1/2 is -1. We add 1, we do indeed get 0. So that completed the inner circle. Okay, and that's from 2 pi over 3 to 4 pi over 3. So we end up with our upper and lower limits of integration in order to find the area. And that's it. Once you have that, that is the hardest part to the whole problem. Okay? Because then all you need to do is just plug in the 1/2, plug in the function. R was 2 cosine of theta. I'm going to need space, so let me erase a little bit here. There we go. I don't need my whole chart. Cosine of theta plus 1 squared, because it's 1/2 r squared d theta. Okay, and like I said, you're going to plug this all into your graphing calculator, and it's going to give you that it's approximately 0.544. And that is the answer. Okay, don't forget approximately and round to 3 decimal places, and you get your answer. It's a really small area, but it makes sense because it's only the inner loop. Sometimes it's called the smaller loop because, you know, the outside would be the big loop and the inner one is the smaller loop. So just a little heads up for the future. All right, good luck.